This video is part of an online course of multivariable calculus, and I'm going to talk about divergence of a vector field. So let's take a vector field F with the coordinates P, Q, and R, where P, Q, and R are functions of X, Y, and Z, and I'm gonna define an operation that is called del. So del operation, which I'm gonna show it by delta like that, and it's kind of a notation wise. It's an operation. Derivative with respect to x. It's a vector with the coordinates that are derivative with respect to x, derivative with respect to y, and partial derivative with respect to z. Okay, and so if del operates on a function, then we get the gradient vector. If we have del cross product with the vector field, we get the curl of the vector field. And then if del has the dot product with the vector field F, this is called divergence. We show it by that. Okay, so div F, which is divergence of F, would be partial derivative. As you see, it's just a dot product, right? So it would be the dot product of P, Q, R with the del vector. So it would be partial derivative of P with respect to X plus partial derivative of Q with respect to Y plus partial derivative of R with respect to Z. As you see, divergence is a scalar quantity. So gradient is a vector, curl is a vector if it is in space R3, and divergence is not a vector, is a function. It's actually a scalar. It's a function. Okay, so I can say divergence of F is the del operation with F, and its derivative with respect to X. As I said, it's like the notation wise, derivative with respect to Y and derivative with respect to Z, dot product with P, Q, and R. That's why we get this. Let's look at one example to see how it works. So example 1, divergence of a vector field F, where the vector field F is negative e to the xy. The second coordinate is xyz, and the third coordinate is ln x z squared. Okay, so I can say that the divergence of F is partial derivative of negative e to the xy with respect to x, partial derivative with respect to y of xyz, and partial derivative with respect to z of ln x times z squared. Okay, so with respect to x, this is negative y e to the x. With respect to y, derivative of that, it would be xz, and with respect to z, this is just 2z ln x. As you see, we get a function of x, y, and z. It is not a vector, it's a function. So we can check our work and see that we get it correct. So an example 2, I can say that the divergence of curl of F is what? Let's calculate curl of F, and then we're gonna get divergence of that. So curl of a vector field F is determinant of this matrix ijk, the del operation, because curl is actually the cross product of del operation and the vector field F. So derivative with respect to z, with respect to x, with respect to y, and then with respect to z of p, q, and then r. So curl is a vector. It's just because it's a cross product. Cross product of two vectors is a vector. The first coordinate would be r with respect to y minus q with respect to z. The second coordinate, I'm going to remove the row and column containing j. It would be r with respect to x, so negative r with respect to x plus p with respect to z. And then for the third coordinate, I'm going to remove row and column containing k. It would be q with respect to x minus p with respect to y. So I get a vector. Now let's find divergence of curl of f. So for the divergence, all I need to do is to take partial derivative of that with respect to x of the first coordinate, or y minus qz, plus partial derivative with respect to y of pz minus rx, plus partial derivative with respect to z of the third coordinate. Okay, so I get ryx minus qzx plus pzy minus rxy plus qxz minus pyz. Okay, so let's look at here. Ryx and rxy, they're equal to each other. It's just because we take derivative of r with respect to y and then x, and since rn is a continuous function, we have that. This one and that one, they go away with the same reason, and this one and that one, it goes away, so I get 0. 0 here is not a vector, it's a function, it's just a scalar. Very good. It's a nice theorem that the divergence of curl of f is 0. Example 3, it's divergence of gradient of f. So f is a function. With this notation here, I have gradient. Okay, so I can write that gradient is a vector, and I have for divergence, I have divergence dot product with the vector field, and I have gradient vector field here. So see what I have. It's a dot product of the del operation with respect to x, with respect to y, and with respect to z of the gradient, which is fx, fy, and then fz. You see what I get? It would be partial derivative of whatever that I have as my first coordinate with respect to x, so it would be fxx plus the partial derivative of that with respect to y would be fyy, and partial derivative of this with respect to z, fzz. Okay, this is actually, you see, another notation that I can use for it. It would be del square of the function f. This is famous. This is called Laplacian. And Laplacian in physics appears in wave equations or heat equations. So Laplacian is actually divergence of gradient. And as you see, we use Laplacian a lot in physics. So Laplacian here is actually divergence of gradient vector field, and I'm gonna change the color of this one just because these questions are very important, these examples. Now let me give you just one small note about the divergence, and I'm gonna say a little bit about the physical interpretation. Let's take F as the velocity field of a flowing fluid. Then divergence of the velocity field would be the volumetric dilatation rate of a fluid particle. It's actually the physics name for the divergence, but in physics they use that. But I can say that it's actually a rate of change of volume of the fluid. Okay, that's for divergence. So divergence basically measures how much the fluid F expands. Well, if expands like this, it means that the divergence of F is positive. If it contracts, so it is contraction. If it contracts, then the divergence of F is negative. So we have a sink here, we have a source in here. That's basically just a little bit about the physical meaning of divergence of F. It is rate of change of volume of the velocity vector field.